Good morning, and today we'll be starting one of the calculus topics for higher maths, and we'll be looking at differentiation. So let's do an introduction to differentiation before we start to learn the process of differentiation. So don't copy this as a note, please. Okay, as I said, differentiation is a branch of calculus, and calculus is the mathematics of motion and change, generally divided into two parts. We're looking at differential calculus, that's what we call differentiation in this part of the topic. And that's the part of the topic that deals with calculating rates of change, defining slopes of curves, and calculating velocities and acceleration of moving objects, etc. Okay, the other aspect of calculus is integral calculus, and we'll be doing a topic integration later on in the higher course. That deals with problems of determining a function from the information about its rate of change, so it's a kind of a backwards question coming from the rate of change. It enables us to calculate the future location of a body from its present position and a knowledge of the forces acting on it. And it enables us to find areas and volumes, lengths of curves, and masses and volumes of some arbitrary solids. Okay, so we're still not copying this as a note just yet. The derivative function is a measure of the gradient or the slope of a function at any given point. And this requires us to consider the gradient of a line. So we're going to be looking at this initially as the rate of change within a graph, which is the gradient. Okay, it's a very common rate of change. The gradient of a graph is the rate of change of the y values compared to the x values, isn't it? So we know that the gradient is the difference in y's compared to the difference in x's. So it's the change in y divided by the change in x. And that's where your y2 minus y1 over x2 minus x1 comes from. Let's look at this graph which shows the movement of a car over time. And we have the distance in kilometres on the vertical axis and the time in minutes on the horizontal axis. So if we want to describe the car's journey, what is the average speed? Well, we'll use a bit of an unusual unit of speed here, which is kilometres per minute, but that's what we're going to look at for this question. What is the average speed in kilometres per minute of the car during the first 10 minutes? Well, that would be distance divided by time, just going way back to your original speed distance time calculations, which would be 1.5 kilometres per minute. The next 10 minutes, and that would be the distance divided by the time for that next 10 minutes, 0.5 kilometres per minute. And then the last 10 minutes would be 2 kilometres per minute. Now we can see here that also just worth noting that the speed is increasing as the slope of the graph is increasing as well. Okay, and the first 20 minutes, there we go, directly from the beginning to 20 minutes in, and we look at the distance there divided by the time there. Okay, that would be a distance of 20 divided by a time of 20. That's why it's 1 kilometre per minute. And the full 30 minutes would be from start to finish. So it would be the average speed there. Okay, so that'd be your 40 divided by your 30, 1.333 kilometres per minute. Now the graph shows the movement of a car over time. So what is the actual speed at 5 minutes from the start? So we could say it's going to be around about 1.5 kilometres per minute, because within the first 10 minutes, the average speed is 1.5 kilometres per minute. At 15 minutes, that's between the 10 and the 20 minutes part of the journey, isn't it? So it's going to be around about a half kilometre per minute, and so on. And 25 minutes would be in the third part of the journey. What would be the speed at any time during the first 10 minutes? Well, it's going to be around about 1.5 kilometres per minute. But those are the average speeds. And does a car actually travel in this way? Not really. Okay, it wouldn't travel with those speeds and then instantly changing to the other speed like that. Okay, the gradient of the line is the speed of the car in this particular example. The gradient of the line is a constant in this case. Now, as we have seen from the previous example, the shape of the graph implies that a car could travel at a constant speed and instantaneously change to a different speed. but that's not the way it happens, isn't it not? So we're going to be looking at question 2 in exercise 6a to show this. Now that's question 2 of exercise 6a. That would be a more realistic graph of a car's journey. It would be travelling in curves. It wouldn't just be straight edges that would just change from one speed to another instantly. It would have to gradually change. And we can see that, yes, the average speed here is 1.5 kilometres per minute, but the actual speed at any particular point of the journey changes. We can't say that we can see exactly what the exact speed is 5 minutes from the start. Without using this process of differentiation, I'm going to show you. So the process of differentiation allows you to be able to work out instantaneous speeds. So for example, I'll be able to tell you then what the exact speed is at that point of the journey, what is the exact speed there, and so on. And that's what we're going to be learning how to do. How can we find the gradient of a curve if it keeps changing? Okay, so we know that the speed in this context is the same as the gradient. So let's look at the graph y equals x squared. Here's the right hand side part of the graph, okay? So y equals x squared. Here we have the distance and the time marked on the axis. So if the average speed over a given interval is equal to the gradient of the line joining the points in the curve, we know that the average speed is the same as the gradient. That's the average speed between those 2 points there. We could work out from the distance divided by the time. But what if we actually reduce the time interval and bring the line down like that? It's getting closer and closer to the actual line of the curve. That brings the line down again. Look how close that is getting to the actual line of the curve and the slope of the curve. So the line that we're getting from approximating the straight line onto the curve is getting closer to the actual gradient of the curve. And the closer and closer we get, the more the gradient of the straight line is similar to the gradient of the curve. And that's going to allow us to then eventually find the instantaneous speed. We call that f dashed of t at any time, and it's equal to the gradient of the tangent at that time. Now this is all just introducing the concept around differentiation and what it means in terms of rate of change, etc. Okay, but now I'm going to introduce you to the method for differentiation, and then we'll go back to the context of rate of change and speed and instantaneous speed and so on, and being able to work out the gradients of tangents to curve and so on. We'll go to those contexts a bit later on once we've learned the process. So let's copy this now from this point here. The derivative of x to the power of n. F dashed of x is equal to x is called the derived function or the derivative of f of x. So f dashed of x is what we call the derivative of the original function f of x. The derivative of the function represents the rate of change of the function, the gradient of the tangent to the graph of the function. The process of deriving f dashed of x from f of x is called differentiation. Okay, so that is what we're going to be using for the notation for this. Now the rule for differentiation is that f of x is equal to x to the power of n. Then f dashed of x, which is the derived function, the differentiated function, is n times x to the power of n minus 1. So this n was the power originally, and it now becomes the multiplier. And where we had n, we now have n minus 1. So what we are actually doing to differentiate a function is we are multiplying by the power and we are subtracting 1 from that power. That's the process of differentiation. Multiply by the power and subtract 1 from your power. Before differentiating, ensure you express the function in that form x to the power of n. And I'll show you some examples where it's not expressed like that and we have to change it. So copy this example down. So it starts off really nice and easy. If f of x is equal to x to the power of 6, find f dashed of x. So remember, we multiply by the power and we subtract 1 from the power. That's your rule down there. You don't have to write that every time. That's just popping up as a reminder. But f dashed of x is equal to 6x to the power of 5. Multiply by the power, subtract 1 from the power. Okay, if f of x is equal to x to the power minus 2, what would f dashed of x be here? So we'll do the same thing. We'll multiply by the power and subtract 1 from the power. Now be very careful when we subtract 1 from the power, because you have to be careful with your negative numbers. Negative 2 take away 1 is negative 3. Okay, so minus 2, negative 2 is your coefficient, your multiplier, and your new power will be negative 3. Now we could rewrite this. This is actually a fine answer to leave it in, a fine form to leave the answer in. However, we can change it back to a positive power, particularly if we want to then go a little bit further later on and put numbers into it. But we can bring the x back down to the bottom and make it x to the power positive 3. Okay, if you're bringing the x down to the bottom like that, make sure you know that the 2, which is the whole number 2, stays on the top of the fraction as still a whole number 2. If you brought the 2 down to the bottom with that x, you would turn the 2 into a half, and you can't do that. It's just the x that can change level, okay? So here we have f of x equals x to the power 5 thirds. This is where we've got to be careful. We have got fractional powers here. So we multiply by the power and we subtract 1 from the power. So the new multiplier is going to be 5 thirds. And what will be the new power? Well, we have to do 5 thirds take away 1. And to do this, we want to think of 1 with the same denominator as we have here. So we're going to do 5 thirds take away 3 thirds. You can write that at the side if you wish. So 5 thirds take away 3 thirds is 2 thirds. So we have 5 thirds times x to the power 2 thirds. Okay, so here we have a negative fractional index. So we're going to multiply by the negative 1/2. And then we have to do negative 1/2 take away 1. So we don't think of it as a 1 when we're dealing with fractions. We think of it as negative 1/2 take away 2/2. Negative 1/2 take away 2/2, which is going to be negative 3/2, 3 over 2. Now, how could we tidy this up a little bit further? We could bring the power, we could bring the x down to the bottom to make the power positive, to make the index positive. And if we were going to do that, we're going to bring the x down to join the 2. The 1 stays in the top, the negative stays in the front, and the x goes down the bottom and becomes a positive power. Now we can go even further and turn that back into a surd again, but we'll be dealing with that later on too. Okay. Now that answer there is actually the answer differentiated, and that one is absolutely fine to leave it like that. We do have to practice getting them back to this stage because we do have to be able to substitute numbers into it. Now remember I said it has to be in the form x to the power of n before we can even differentiate. This is an example of that. So we don't have x to the power of n, meaning the x is in the top with just a power. X is in the bottom just now. So we're going to have to bring x up to the top before we can even differentiate. So sometimes you have to fix up your function before you're even ready to differentiate the function. So remember, x is going to come up to the top. The power of that x on the bottom is an invisible 1. So when you bring it up to the top, it will be x to the power negative 1. You're going to now multiply by that power and subtract 1 from the power to do f dashed of x. So we haven't written f dashed of x yet because we've only just fixed up the function. We're now ready to do f dashed of x because we're now ready to multiply by the power and subtract 1 from the power. So we have minus 1 x to the power negative 2. And then we're going to simplify that. Now, we could either leave it like this by taking the 1 out, minus x to the power minus 2, or bring the x down to the bottom, which would be negative all over negative, 1 in the top, and the x to the power 2 is now in the bottom. Okay, given f of x equals square root of x, find f dashed of x. So again, that has to be in the form x to the power of something. So you need to remember what the square root is as a power. Okay, now you may remember the square root as being the power of a half, but let me remind you why. There's an invisible power here, which is a 1, and there's an invisible number outside that root sign, which is a 2. And when you turn surds into fractional powers, it's always that number over that number that becomes the fraction, the power over the surd number. And there's an invisible number there and an invisible number there, which makes that a little bit harder. So that's x to the power 1 over 2. Okay, that's an x to the power of 1, and that's the square root. And because it's the square root, which is the first root that we have, we don't have to write the 2 outside it. When it's a cubed root and so on, we do write the 2, the 3 and so on outside it. But for a square root, we don't have to. So we haven't differentiated yet. We're now ready to differentiate by writing f dashed of x equals, we multiply by the power, which is a half, and we're going to subtract 1 from the power. So we're going to do 1 half minus 2 halves, which is minus 1 half. Then we can bring the x back down to the bottom, which makes it 1 over 2x to the power positive a half. So the process of differentiation is really not difficult. It's multiply by the power, subtract 1 from the power. What makes differentiation difficult is National 5 knowledge of indices and surds, and also being able to manipulate fractions and negative numbers carefully. That's what makes people make mistakes. So fractions, negative numbers, be careful with them. You learned them way before National 5, that kind of thing. But the indices and surds is a big thing too. Make sure you're careful with that too. Don't throw away marks because you don't have the knowledge from National 5. Okay, so what about this one here? So we have to fix it up first of all. We have to turn it into a fractional power, and then we have to take that x up to the top. So we'll turn it into a fractional power first of all. Remember, that's an invisible 2 out there, so that'd be a 5 over 2. And then we take it up to the top by making x to the power negative 5 over 2. We haven't even differentiated yet. So we're now ready to differentiate and write f dashed of x. So f dashed of x is negative 5 over 2 as your multiplier. And then be very careful here. So we're going to have to do negative 5 over 2, take away 1, which would be negative 5 over 2, take away 2 over 2. And negative 5 take away 2 is negative 7. So it's a negative 7 over 2. So be very careful. Now that's it differentiated. We could leave it like that. Or we could take it a little step further and bring it back down to the bottom to join the 2 on the bottom and make it an x to the power positive 7 over 2. Okay. So we're now ready to do exercise 6D. And we've got quite a number of questions there, okay, on exercise 6D. Now, as always, ask your teacher if you need any help. Now, it looks as though there's lots and lots and lots of questions, but you do every one of them very quickly, and some of them you have to obviously convert the function into x to the power of n to begin with. Now what you'll see in exercise 6D is that they don't start with f of x equals, so they just start with the function like x to the power 7 and so on. So as good practice, can you do these questions in the same way we were doing them in the examples and write f of x equals, so the first one would be f of x equals x to the power of 5, so you're getting into the habit of writing the notation for differentiation. So then you would write f dashed of x equals, and then you would answer your question. Okay, so good luck. Ask your teachers if you need any help, and take care. Okay, bye.